Hi everyone, in this video, let's create a machine learning algorithm called support vector machine that can be used in predicting the stock market value of a particular company. So, before getting started, we need a data set that can be used in training our model. So, I got my data set from Kaggle. So, if you don't have a Kaggle account, please register to it and make use of the data sets that are available. I'll be using Python and Jupyter Notebook for this project. And I'll be using a number of libraries for this project, such as Numpy, Pandas, Matplotlib, Seaborn, and SkLearn. And regarding these libraries, Numpy is used for dealing with higher dimensional arrays and numeric values. Pandas can be used for data analysis and manipulation. Here we will be dealing with Pandas a little bit more in the video. And Matplotlib and Seaborn are mainly used for data visualization. SkLearn, also known as scikit-learn, that has a number of machine learning algorithms that can be used for classification and regression. SkLearn is one of the libraries in Python that can be used for creating machine learning algorithms. So, in this project, I already got the data set as said, and I have pre-processed the data. I pre-processed the data such that only important features are present, and there are no null values and outliers in the dataset, making it less complex. So initially we will read the dataset. So here I am using pandas to read the dataset. So I am assigning a value called data and assigning the dataset to this value, to this variable. So I am giving pandas.readExcel and giving the path of that particular dataset in my local machine. Pandas has the ability to deal with CSV files and Excel files. So it is important to note what type of dataset you are having, and it is important to add the extension at the end of your path. So here I am giving the name called stock market 2022 as the dataset contains only the records of the year 2022. I have given this name. So we are reading the dataset. So we got the dataset in the name of data, and we can see here there are features like date, open, high, low, close, adjacent close, volume, and ticker. These are the important features when we deal with the stock market dataset. So we have the data that has the dates from January 1, 2022 to December 30, 2022. That means it has all the business days records of that particular company. It has open values, high, low, close, and adjacent close. Adjacent close is mainly used by investors to know more about the historical data about the particular company. Volume is the number of transactions, that means number of shares that has been bought and sold on a particular day. Ticker, every company will have a particular symbol in their name. For example, Microsoft will have MSFT, and other companies have their own ticker in the stock market. So this is the data set we are having, and we are going to predict the close value using our model. So this close value is mainly dependent on these values: open, high, and low. So close is dependent on these features as per the dates. So we will not be using adjacent close and ticker much in this project. And volume plays an important role in the close value, as we know that uh, the number of transaction increases, the value of the particular stock will have a chance to rise or low. So we will be dealing with that. So let's not get much into the stock market things, and let's go on to our model that can be used for prediction. So as you can see, these values has more number of digits after the decimal points. I have to get only 4 decimal values after the decimal point. So I'm getting the column values in an array, and I am declaring a variable decimal places with a value of 4. So I'm using numpy to round off the values. In numpy there is a function called round where we have to pass two parameters: the columns that has the values and the number of decimal places. If we do this, we can get the required number of decimal places after the decimal point. As I said earlier, the adjacent close and the ticker values does not impact the close value. it is independent. So we are not going to use adjacent value and ticker here. So what I'm going to do is I'm going to drop these columns. So I'm creating an array of adjacent, close, and ticker, and I'm using data.drop. So this is the dataset name, and I'm using drop method to delete these columns. So we have to pass the column names and in place is equal to true. So what does this in place equal to true is that it does not create a new dataset. It alters the existing dataset. So if I give in place is equal to true, this dataset that has been named data itself gets changed into the required statement. So it does not create a new dataset. That's why we give in place parameter. And furthermore, I need these columns in an orderly manner such that it is easy to understand. So what I'm going to do is I'm going to change the columns order. So first I need data, then the open value of the stock, low and then high, and then I need the volume and close. It's better to keep the close value that's being predicted in the last column. So we are altering the columns in our data set. And furthermore, this date in the data column is in the string format. And I need to change that into date, month, and year format. So for that, Pandas has an inbuilt function called toDateTime. If we pass this date to that function, it formats the string into datetime format. And furthermore, we have a method called string format time. If we give the specific syntax, it gives the date in this manner. So let's execute these statements. So we dropped the adjacent column and ticker values here, and now we are going to format the date. Now it's been changed to the required value. And as I said, there are no null values in the data set and outliers. Outliers will be easier to explain when we visualize the data. So now we are going to use Matplotlib. So what I'm doing here is I'm plotting the open value and close value of the particular data set. So when the days goes along, this Matplotlib plots the open and close value respectively. Both the open and close value will be in the same chart so that we can compare what happens when the stock is being transacted to the further days. And here we are going to see the low and high value of the same dataset so that we can compare how these values change according to time. As we can see here, the open and close values, they are both almost in the same line because there are no much differences in the data. And as we can see, the data is increasing linearly. You can see that the data is being increasing linearly along with time, and this also represents the same. As we can see, the data is in a linear manner. It goes down and it increases high. So it is better to use support vector machine for regressions here. For this support vector machines for regression, we need to get the understanding of linear regression. It is better to have a prerequisite of linear regression algorithm for better understanding for the support vector machine. So when we look at these graphs, we can observe that there are no outliers. To get a better understanding of outliers, let us consider this situation like this. So we have a graph like this. So let us consider a graph, and we have data points here, 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 and here. So we are trying to draw a best fit line such that the distance between the best fit line and the data points should be minimum. So what happens if an outlier is present? Let us consider this as a linear regression model. So if an outlier is present, say it is present here, the best fit line tends to move towards the outlier. Since this is an irrational value here, it will make the best fit lines make it tilt towards it. So in this case, what happens? Let us consider a data point that has been here. So it will move towards it. So this makes our prediction to be wrong. See, the value increases exponentially here. Instead of other data points that are here, it is predicting incorrect values with this best fit line. So it is necessary to remove the outliers in our dataset. So we have to pre-process it when we are getting the dataset. So now let's get back to our code and see what we have in our graph. Here we are going to plot the volume of our dataset. Now we can see that the volume during the first 50 days peaks at the day 50, and eventually the volume reduces and it peaks again at the day 150. I mean, it's almost over 5 months after 2022, and again it gets the maximum value at the day 200. So it is necessary to note that the volume of our stock market value is increasing periodically. Here we have to make sure that our model gets trained in volume 2, because eventually again there are chances that the volume of the particular company's stock may go high. This may affect the close value respectively. So it is an important aspect to note the volume changes. And moreover, we are going to do the train test split of our model. So before creating any model in machine learning, it is important to split the data into training and testing data. Now we are going to do the train test split. So now I am declaring a variable called AX and I am passing a two-dimensional array. As we can see that these features open, low, high and volume, they are a two-dimensional array, and I am declaring a variable Y and I'm declaring the close value of the dataset. It is a single dimensional array as it contains only one row of data, whereas these values are a two-dimensional array. We imported the train test split in the beginning of the coding. Now, when we pass these data to the train test split, it will assign these values respectively. The main objective of our model is to predict the value in the future. For that, we need to do train test split. So what does this train test split do is that it takes a part, it takes a part of the subset of the data set. The major part of the subset goes to training and the minority of the subset goes to the testing. So here when we give the test size as 0.2, what it does is it takes 20% of the data set. That means if a data set has 100 records, 20 records of the data will go for testing and remaining 80% of the data will be trained in the model. And random state equal to 42. So what does this random state means that if I have a data set and I am doing train test split, we don't know which records will go for training and which records will go for testing. If you have a data set and I have a data set which are same, and we give the random state as the same value, we both get the same training dataset and testing dataset. If we give different values, the records will be interchanged. So there is not a possibility that we get the same records. So if we give the same random state, we can get the same records of training and same records for testing. So we have to do the train test split in this manner. So I am executing this. We can see that the training shape is 200 records and 4 columns as we gave. These are the 4 columns that has 200 records. Since our dataset has 251 records, we can see that 200 records with 4 columns has been trained and the remaining 51 records with 4 columns for test. And in the same manner, we have 200 records trained for that close value and 51 records are kept for testing value. The testing data will never get trained during this. So let's see what is there in Xtrain. Those 4 records. This has 200 rows and the Xtest should have 51 records with 4 columns. These records are kept for testing so that we can get the performance of our model. If we trained in the entire records, there won't be any record to test it. So we cannot determine the performance of our model. So it is necessary to split the data into train and test. So let's see what there is in train. So we have trained these records and kept this for testing. This is the main purpose of train test split. The main purpose is to give the records for training and keep the records for testing so that we can get the performance of our model. So now that our train test split is complete, now we can go further. Once this is done, we are ready to go for our model to be created. All the data pre-processing has been done and the data set is ready and it has been done the train test split. Now we are ready to implement the model that we are going to make it predict. So now let's import the required libraries to implement our model. We will import the support vector regression and metrics. In this metrics means it's a method to calculate how well our model performs. And for pre-processing, we will be using standardization from this library called standard scaler. So before jumping into this, we will have a look at support vector machines and how it works. So now I'm executing these libraries. So now coming to support vector machines. Support vector machine is a supervised machine learning algorithm used for both classification and regression. Here we have a supervised data. That means it is well defined with rows and columns. As we see, we have different features with different row names and columns. So it is easier to train this data set with support vector machines. What support vector machine does is that it creates a hyperplane that separates data points. To make it simpler, let's visualize how support vector machine works. So here we can see the support vector machine works like this. The red line we can see here is the best fit line, like linear regression. Unlike linear regression, support vector machine has two lines that is called as marginal lines. These lines are at a particular distance away from the best fit line. What support vector machine does is that it creates these two lines called marginal lines and tries to get the data inside those lines. It will be as much as near to the data points so that during regression it won't make any errors. The distance between the best fit line and the marginal line is called the marginal distance. This distance can be altered according to the data points that we have. So if you look at this, blue color is a separate set of points and green color are different set of points. What support vector machine does is that it creates a hyperplane. This is a two-dimensional image. Consider it to be three-dimensional. The blue points are above the green points. So support vector machine creates a hyperplane between these two data points. So we can easily classify blue points above the support vector and green points below the support vector. But here we are doing regression. What support vector machine does? It does to place the data points inside these marginal lines or near to it so that the distance between the data points and the marginal lines are minimum. If the data points and the marginal lines distance is minimum, implies that the data that has been present and the data that are going to be present are always near to the marginal line. This way we can reduce the error. So we have a similar case in our data set too. We have visualized the data in our data set where the data keeps linearly increasing. So the distance between the best fit line and the data points are always minimum. Let us visualize this in a three-dimensional plane. So here we have a three-dimensional image. So just look at this. The blue points above were like this. So the data points are above the hyperplane and the green points are below the data point. So we can see that the SVM creates an hyperplane between them. We cannot see the marginal lines here, but the marginal lines will also be present here. So the distance between the data points and the marginal lines are minimum. This is what support vector machine does. This is an example of linear support vector regression model. Actually, there are several versions of support vector machine. We will discuss about that. We can use this model when our data is linear. So what happens when our data is non-linear? For that, we have different kinds of support vector machine that can be used in specific cases. Now let us go back to our code and let's discuss what we can do there. So here I have created a support vector instance of the support vector machine class. This instance create a model that we can use. So before going to that, let us discuss about standardization. Now I am creating an instance of standard scalar inside a variable called scalar. So what standardization is? Standardization is a process that needs to be done before we process any machine learning algorithm. This process enables the computer to understand the values of our features more. It increases the performance and stability. This standard scalar converts our feature values to values that are between 0 and 1. So it transforms it creates and transforms our feature values into values that are between 0 and 1. There is a similar process to standardization called normalization. These two are similar processes that are used for enabling and transforming our feature values into values that are between 0 and 1. This makes our system and algorithms to understand the feature values to a better understanding. So let us get into mathematical institution of standardization and normalization. Standardization is here and it is given by this formula. Standardization always involves with the mean value of the features and standard deviation between them. X is our data value. We have to separate with the mean and divided by standard deviation. This gives a value between 0 and 1. This process will be done for all the features in our dataset. Whereas normalization does not involve with mean and standard deviation. It only involves with a min and max values of our features. So let us consider a feature that has values between 10 and 1000. For humans, it will be easy to interpret the data and process it. But whereas these algorithms and machines have to make use of this normalization and standardization so that it increases the efficiency. And there is one more point with standardization. It is always better to use standardization when the features in the data follows Gaussian distribution. Gaussian distribution is nothing but this bell-shaped curve where these data are aligned in this manner. But our dataset has features that has the values that is linearly increasing. So it's better to use normalization. But we are going to try how standardization works and how it increases the efficiency and what is the performance and its output. Let us discuss about this mean squared error and R square later in this video. Now let us go back to our code and let's have a look on how our support permission works with standardization. Here I am fitting this scalar object and making the trained data into another variable. So the trained data we got from train test split, we are making it to standardization using this object and we are assigning to this variable, and the same process is done for testing data. Now we are creating an SVR model. Here I have given the kernel RBF. Previously we had a look on how linear SVR looks like. This is what linear SVM looks like. But what I gave here is RBF. This is a different kernel. This does not work linearly. So what the point here is, support vector machine can also be used for nonlinear data. There are several types of SVM model as we said. So let's have a look at how RBF looks. So let's have a look at how RBF works. Now let us consider our dataset. Here we have data points like this. Here a data point, here is one data point, and here is another data point, and here is another. So what we done is we have easily created a hyperplane between them. So we can easily classify and do regression between them. So this is not a problem with linear dataset. So consider a dataset where all the data are nearby like this. So these two are separate data and the data surrounding them is different. So what should we do in this case? The data that is inside this circle, wait a minute, the data that is inside this circle these data are separate and the data inside them are different data. Now, how do we classify this? For this, support vector machine has a separate kernel to handle this kind of situation. So let us discuss how support vector machine handle that. To handle this, support vector machine has a kernel called RBF. What RBF is? What RBF is? So RBF is radial basis function. So what this radial basis function does is that it classifies these set of data and projects them into three-dimensional space. In the left diagram, what we are seeing is a top view of the data where we cannot linearly separate. We cannot draw a line between them, and if we draw a line between them, it wouldn't make sense and it does not classify the data. What support vector machine does is that using this RBF kernel, it projects the separate data into a higher dimensional space. Consider this from the top view. It will resemble the same. But when we see in a three-dimensional space from another angle, the data in the plane are different and it projected the other data into this. So we can easily classify and do regression in them. Consider this as a pyramid. The pyramid from the side looks a way tall and it makes a three-dimensional image. But whereas from the top view of the pyramid, we can only see the four edges and the center point of the pyramid. From there, we cannot do regression or do classification from there, and it is not possible to draw a line between them, and the hyperplane would not fit into that data points. So this is where the RBF comes to play. So here we can see, right, the data, consider these numbers as data points. -10, -8, -6, -4, 4, 6, 8, 10 are the data points that are on the plane below the other points. The SVM projects these data points in a three-dimensional plane. So this way we can do classification and regression easily. So we are doing that kind of function in our linear space, linear data set. This is not necessary, but we are going to try how standardization and RBF, these both are not similar to the data set that we have, but still we are going to test how this SVM is going to work on those. And coming to these hyperparameters, let us discuss that. The C parameter in the SVM represents the penalty for misclassification. A smaller C creates a wider margin but may allow more misclassification, while a larger C leads to narrower margin but fewer misclassification. So the value of C is necessary for the correct classification and regression that we are doing. So it is best way to practice the optimal value for C. It should neither be high nor be low. It is one of the best practices to decide the value of the C while we are creating a machine learning model. The epsilon equal to 0.1 implies that epsilon is the margin of tolerance. As we saw that the support lines, marginal lines, the distance between the marginal lines and the data point should be minimum. So when we change the value of the epsilon, it adjusts itself so that the distance between the margin and the data points is minimum. If the data point is more away from the marginal line, then it classifies it as error. So while doing regression, it tries to predict the data such that it is in the minimum position from the marginal line. So the value of the epsilon plays an important role in the marginal distance between the data points and the marginal line. So these are the hyperparameters that we are creating while we create our model. After that, we are going to fit the data model, the trained data, and the value that we are going to predict. So SVR underscore model fit. This line of code fits the data that we processed into the model. Then we can go for the predictions. This statement dot predict is an inbuilt function where we can give the test data to it. So this test based on our trained data inside the model. And to see the accuracy of our model, we can use various metrics. Now I'm going to use MSE. MSE stands for mean squared error. And we pass those parameters, the testing data and the predictions that we made. So when we see the mean squared error and how it works is that The basic principle of our model is to make the distance between the data points and the best fit line minimum. So how the mean squared error works? It works based on this formula. The y is our actual data value and y cap is the predicted value. So n is the number of data points that we have. So it squares the data value. Basically, we can see that this is an equation. This equation leads to a parabola. It is a minus b whole square. So that when we use this formula, we can get an parabola where the error is minimum. This is the global minimum. So only one minimum value is present here. So when we do this mean squared error, it gives an minimum error for the model that we created. So from this we can understand that when the mean squared error is very less, then it means that we have created a good model. So try to running this. It will. So we can see these are the predicted values and the mean squared error is 0.11, which is pretty good. So this is how the mean squared error is working. And there is one major disadvantage in mean squared error. So in case if there is an outlier, consider an outlier like this. So our data points are like this and there is an outlier. So the best fit line goes away like this. If the data point of outlier is here and all the best fit line move towards it. So the predictions of the data will be higher rather than the actual data point. So this leads an error in the predicted values. So if the predicted values are high, then the difference between them will be high. So the mean squared error will have a larger value than the actual value. So mean squared error will not work fine when there is even a single outlier. So it is important to pre-process the data without outliers when we are proceeding to use mean squared error. This is one of the major points that we have to remember when using mean squared error as a metric in our model. So as we can see, these are the predicted values for the tested data. If we map them or plot them, we can see the difference between them. It is a best practice to visualize the data that there are actually present and the data that we have predicted so that we can see the difference between them and how well our model is working. So again, there are various metrics to measure our data. I have used mean square error above and mean absolute error is there and R2 score. So let us again do this and we can see the mean square error. So now we can try different things. So previously we have done standardization. What about normalization? And regarding this, we have used the kernel RBF and C equal to 100 and epsilon equal to 0.1. How do I know that these are correct? There are various kernels such as linear, polynomial, RBF and sigmoid. So how do I know which model should I use and which model gives me the best accuracy? For that, we have to do cross testing. We have to try different kernels with different C values and different epsilon, and then only we can come to a conclusion that which model works perfectly with which kernel and which cost function and which epsilon. So we can do that here. Instead of standardization, I'm using normalization here. Min-max scalar is best for normalization, and again I'm importing mean squared error here, and I'm using grid search CV. Also known as grid search cross-validation is a technique used in machine learning to search hyperparameter for a model. That means grid search CV helps us to find the best hyperparameters for our model. Here, now after importing normalization from SkLearn, we are fitting our data from train test split into that normalization function. So here we are giving the param grid. What param grid is? Param grid is a dictionary of values that has key as hyperparameters and the respective values that could be best suit for our model. Now we are creating an instance of the regression model. So here we are giving grid search CV, SVR for that instance and param grid. Param grid is the dictionary values that we gave here. And CV is the number of cross validations and scoring. What this scoring does is that for various combinations of these parameters, it will give a score based on the performance of our model. So for example, consider linear and C50 and epsilon 0.2. If this combination is performing better, then the score of that particular combination will be high. So from that, the param grid will choose those parameters, and end jobs in this parameter defines the number of CPU cores that are used for calculating this particular performance. If n jobs is high, the number of CPU cores will be high. That means many CPU cores will run parallelly so that the job can be done instantly. So since this is a smaller case, we are giving n jobs as 1. So now we are giving the normalized trained data to this grid search. So this best params, we are assigning a variable called best params. What this best params is that after the grid search performs, we will be getting some best combination from these. So grid search CV is one of the best methods to choose the hyperparameters. Hyperparameters plays an important role in every machine learning algorithm. So it is always a best practice to do this grid search CV for our models and find the best combination of the hyperparameters. And regarding this kernels, there are different types of kernels. We have taken a look at RBF and linear. Let's have a look at another types of kernels in SVM. So if we come across this, here we can see the 4 different types of kernels in SVM. So this is RBF. The dark blue line is called as RBF. We can see that it proceeds to an hyperplane, and linear is this light blue color, and this another line is polynomial. There is another function called a sigmoid, where there are multiple curves in a same dataset. Sigmoid is a rare case of events that SVM can use. These three are major, and here we have seen RBF and linear model. So we have seen that RBF, we can already created a model, and the mean squared error was 0.11. Now let us see what grid search CV says us, that which combination of hyperparameters is best for our model. So we are giving linear and RBF in the kernel, and polynomial, it is not respective to our dataset. We have seen linear from the visualizations, and we have tested for RBF. And now let's proceed that best SVR model. And here we are passing the best params to our model. These two stars represents that we are passing a dictionary here. What the dictionary means, the param grid, here we have defined a dictionary. The dictionary contains key value pairs. The key as hyperparameters, and the values from those hyperparameter values. So this will be passed as a dictionary to our model. After that, we are fitting the model with our normalized data and training data. Then we are making predictions using this predict method to our test and normalize. Now we are testing the data. No, actually we are predicting the data based on our test data. So again, we are calculating the mean squared error for our data. And if we run this, we can see the best hyperparameters and the mean squared error of this. It is executing. So let's wait till it's executed. As far as I know, that RBF is not best suited, and as we see the visualizations, the data set is linear, and the kernel should be linear, and the C function should be reduced, and there will be a change in epsilon value as well. As epsilon is the marginal tolerance, the marginal tolerance should decrease. Yeah, as seen, the C value has been decreased, and the best hyperparameter for our model is C equal to 50, and epsilon is 0.2, and kernel is linear, and RBF is not used. Since the performance of RBS is not required here, that grid search CV made a linear as our model, and the mean squared error has reduced even more. So here previously we got 0.11, and it is reduced even more to 0.04, which means our hyperparameters has changed, and this has increased the performance of our model. And to confirm this, we can use another metrics called as R2 score. What is R2 score? R2 score is another type of metric that can be used to determine the efficiency and performance of our model. And the R2 score is shown as 98.9. So which is a pretty good model that we have created. And let's see how R2 scoring works. R2 is the sum of squared residuals, 1 minus sum of squared residuals and total sum of squares, which means sum of squared residuals means the squared difference between the predicted values and the actual values. And what total sum of square means, it is the sum of square difference between actual values and the actual values and the mean of the actual values. So this line represents sum of square difference between actual values and the mean of the actual values. So if we do this, we will get an R2 score of our model. If R2 score is closer to 1, then we have created a pretty good model. This is an interesting metric that we can use for our models. So here is an R2 score of 98.9, which is actually a good model that we have created. There are also some cases if the efficiency and performance of our model is too high, then there are chances that our model is overfitting. Overfitting in the sense that our model has a more accuracy and it predicts the data exactly, which is not necessary. There are two types of things called as underfitting and overfitting. Underfitting is the model that predicts inaccurately, and overfitting is in the case the model predicts exactly. Both things should be avoided when we create a model. Here, the model has pretty good accuracy for the data it has seen. For unseen data in the sense the data that is going to be in the future. Nobody knows what's going to happen in the future. So the data can be miscalculated based on the data that is going to be in the future. Our main goal is to create a model that is optimal to predict the future data. If it overfitting, the data definitely will be wrong. So the data accuracy should be optimal. This underfitting and overfitting can be tested by different train test split and testing the model with different data with the different combinations. So it is necessary to test the data with different train test split and unseen data. So we might create a new data set with feature engineering and with the different features added or reduced. We have to test this model whether it is performing and well, and the efficiency is good and the accuracy is also good. So here we have created a pretty good model that is capable of predicting accurate values, but it is also necessary to test with different cases. Let us jump into this mathematical institutions of these normalization, standardization, and mean squared error and R squared values later. So we have created a SVM regression model to predict the stock market values with an accuracy of 98.9%. So see you in the next video.